So here's the culmination of why we were doing the antiderivatives and how it relates to the area under the curve and how it relates to derivatives is this fundamental theorem of calculus. So the limit definition of computing areas sucks, right? It's like a lot of work. Just like the limit definition of the derivative was a lot of work and a lot of computation and not very practical. You could only do it for very simple functions. What we want to talk about is if I want to find that area or compute an integral, I don't want to do that limit method. Just like with derivatives, we don't use the limit definition of the derivative. We use more practical methods. And the fundamental theorem of calculus is our practical method. Now, this notation might look a little strange to you, but here's the main idea. If I want to find the area under the curve for some function, okay, this is what it's telling me, is step one is find the antiderivative. We'll call it f of x. And the way you read this is this function, this capital F, how it relates is that the derivative of the capital F of x is little f of x, okay? So we found this derivative, right? The antiderivative, like we did before, is to say, you find the antiderivative of that. And step two is you do not have to do anything other than simply plugging in the endpoints and subtracting them. And that will give you the area under little f of x. Okay, that's really cool because it just requires me, rather than doing all that limit stuff, it just requires me to compute the antiderivative and then just plug in the two endpoints and subtract them. That's all it's saying. Okay, so that's it. So for example, let's say I want to do the area from 0 to 1 of x squared dx. Okay, so I want to do this area here. And this is the area under that curve for y equals x squared. And I want the area from, say, 0 here to 1. Okay? And I want this area under the curve here. This area shaded underneath here. Okay, so instead of doing the limit definition like we did in 2 sections ago, in section 2, what we're going to do is we're going to first find the antiderivative by doing power rule. So we add 1 to the exponent, divide by that exponent. And then here's the notation. You're going to put a vertical bar and put 0 and 1. That denotes that you want to plug in 1 and 0 and subtract them. This is simply notation to simply say I'm going to plug in 1 and then plug in 0 and subtract them into that function. Okay, that's what this part here. And then you're going to get 1/3 minus 0, which is 1/3. And that is the area. If you look back when we did this example, you can see that that's how we got that area under the curve there. Is when we did that limit definition. We also would have gotten 1/3. So this is a much faster method. So we're never going to use that limit definition to compute an integral. We're only going to use finding the antiderivative and plugging in those kind of endpoints there. Let's do one more example. And then there's a bunch more examples after this that'll add on. But let's say I want the area of a cosine curve. Let's say I want a cosine curve. Okay, so here's cosine. And I want this area here. And remember, cosine is 0 at pi over 2. So we want that area there. So we're going to go from 0 to pi over 2. Okay, of cosine of x dx. Now, what's the antiderivative of cosine is actually negative sine of x. Or sorry, not positive sine of x, because derivative of sine gives me cosine. And then I put a vertical par and 0 and pi over 2 is just like this. All right. And then we're going to plug in pi over 2 and then plug in 0. Sine of pi over 2 is 1 minus sine of 0 is 0. And I get this area is actually 1. This area is 1. It's kind of surprising that area of a cosine curve is just 1. But there it is. Okay, so we'll do a few more examples of that now. So now we're going to look at the definite integral. And the definite integral is pretty straightforward. All you're simply going to do is you're going to do the antiderivative, and then you're just going to plug in the two endpoints of the values. And that's really fundamental theorem of calculus. That's what it comes down to. So antiderivative is 1/3 x cubed. We don't do the plus c because the plus c is sort of irrelevant when we're finding the area. And you could see it's because the plus c would cancel out, so we typically leave it out. But we write it like this: x equals -1 to 1. And what we're going to do is we're going to simply do 1/3. We're going to plug in 1, so it's going to be 1 cubed. And then we're going to plug in -1 and subtract the 2. That's how fundamental theorem of calculus works. Is I do the antiderivative and I subtract these two. And this is way simpler than doing the Riemann sums for these, right? So this would be 1/3. This would be -1. -1 times -1/3 is +1/3. So plus 1/3, that's equal to 2/3. Okay, how about sine of x? Antiderivative is cosine. Oh, but negative, because the derivative of cosine is negative sine. So I need a negative sign here. I'm going to go from 0 to pi. So I'm going to do negative cosine of 0 minus negative cosine of pi. So that's -1 plus cosine of pi, which is -1, so that's -2. No, that should have been minus. This should have been +1. It should have been 0. I was going to say. One of the ways I do this, if I have a negative sign, the other way I can think of it is I do the negative and then I just do the cosine itself. So I do the negative sign separately. So I'm going to do cosine of pi minus cosine of 0. Cosine of pi is -1. Cosine of 0 is +1. So that's -2, -2, which is equal to +2. So that's the correct answer. So here I kind of messed up. I think I did the order wrong. This is how I would normally do it. I would do the negative sign separately, just put parentheses around the subtraction, and that way it's a lot easier to keep track of the signs. So here I'm going to do the antiderivative. So this would be 1/4 x to the 4th plus x cubed minus 5/2 x squared plus 7x. I don't need the plus c when I'm doing definite integral, 0 to 3. So I'm going to plug in 3. And when I plug in 0, like all of these will be 0. So I don't really need to plug in 0. Like it'll all disappear. Doesn't always disappear, but in this case it will. So I just need to plug in 3. So this is going to be 1/4 3 to the 4th plus 3 cubed minus 5/2 3 squared, which is 9, plus 3 times 7 is 21. So this is 81 over 4 plus 27 minus 45 over 2 plus 21. So this is kind of a lot of numbers. I'll just use my calculator for it. 81 divided by 4 plus 27 minus 45 by 2 plus 21. And that is 45.75. Okay. Here I'm going to do the integral of cosine. So antiderivative of cosine x is sine x. And I'm going to plug in 0 to 2 pi. That's going to be sine of 2 pi minus sine of 0. That's 0 minus 0. It's equal to 0. Now, does it make sense that this area should be 0? Well, this is one period over a whole cosine. And as far as integrals are concerned in terms of area, anything below the x-axis is negative area. Anything above the x-axis is positive area. So this area will cancel out this negative area. So the total area is 0. Because this area down here is less than 0. And it's sort of like symmetric around down the axis, right? So to do the antiderivative of this one, I'm going to use my power rule, but I want to write this as x to the -1/2 so I can apply the power rule correctly. So I'm going to add 1, so it's going to be x to the 1/2 divided by the new exponent. And so that's equal to 2 root x evaluated from 1 to 4. That's 2 times the square root of 4 minus the square root of 1. I treat the 2 separately. So this is 2 minus 1. That's 1, so it's equal to 2. And here we're going to do 1/5 x to the 5th. That's the antiderivative using power rule. 0 to 5. And I'm going to plug in 1/5 5 to the 5th. I can plug in 0 to the 5th, but that's just 0. So I don't know. This is 5 to the 4th, whatever that is. What's that? 25 squared. That's 625. Okay.